Well, let's take a look at atomic structure and electron configuration. I found a brief video that I thought we could watch together to help us remember how to do electron configurations in a very simplified manner that would get the point across pretty straightforward. So let's take a look.
The first thing we need to do to find electron configurations is to find the number of electrons for the element. So we can find this on the periodic table, and we're going to look at the number above the element symbol, which is called the atomic number. That'll tell us the number of protons, but it also tells us the number of electrons. And we can use that number as we try to find the electron configuration for whatever element we're interested in. So we'll move helium over to group 2 since it fits better there for electron configurations. We have our periodic table, and we just need to memorize that every element in group 1 ends in S1, group 2 ends in S2. We'll go over to the P block. Those elements in group 3, they end in the P1, and then P2 all the way up to P6. Going back to the transition metals, we start with D1 and go all the way to D10. For boron, we'll look first at row or period 1 on the periodic table. And we can see that the hydrogen has atomic number 1. It is in row 1, so we're going to write 1 down. That's the period. It's also the energy level for the orbital that we're talking about.
So like he's saying, period 1 refers to this 1 coefficient. S, this is called the S block. It refers to the orbital shape.
We'll go to number 2, which ends in S2. So we're going to call the first part 1s2, and then we're done with period 1. We'll go to period 2, and we see that lithium, atomic number 3, that ends in S1. Next, beryllium, that ends in S2, and those are all of the S's in that second period, or energy level. So we're going to put 2s, and since there are 2 electrons there, 2. Now we're going over to the P block, and we're at boron, which is the element we're writing the configuration for, and we can see that boron ends in P1. Now we're still in the second period, so it's going to be a 2p, and boron ends in 1. So that's it. That's the electron configuration for boron. We'll do chlorine the same way we did boron. In row or period 1, we can see with hydrogen, we'll start atomic number 1, we have the 1s1 and 1s2 full, so we just write 1s2. We go across, and we're actually back in row or period 2, so we have lithium and beryllium, 2s2, that's full. We go over to the P block, and we have all of that full, P1 through P6, so we just need to write 2p6. We go down to row 3, we have 3s1 and 3s2, those are full, so we write 3s2. We're back over across to the P block, and we can see chlorine's there at P5, so we're almost there. So we put 3p, and since chlorine's in the P5 group, 3p5.
So again, you can see how this will fill up in the same way over and over and over again until we get some exceptions and some other ideas. But let's continue on.
That's the electron configuration for chlorine. We'll try one more, vanadium. So vanadium has atomic number 23. So we have 23 electrons, and we're going to go through the periodic table until we get to vanadium. So we'll start in period 1, there with hydrogen, atomic number 1, and we see the 1s1 and 1s2. Those are full, so we'll write 1s2. Now we move down to the second period. We have the 2s1 and 2s2. Those are full. Then we go across, we're into the 2p's, and all of the p's are full. So we'll put 2p6, down to period 3, 3s2. Then we have all of the 3p's. Those are full as well, so 3p6. We're down to period 4, and we're getting close to those 23 electrons that we have for vanadium. So in period 4, we have 4s1 and 4s2. Those are full, so we'll write 4s2. And then we're into that D block there, and if we go over 1, 2, 3, that's where vanadium is, so we would expect that we would have 4d3. However, this is the one exception that you need to be aware of if you're using this method. When we get to the D block, we always take one away from the period number. So instead of 4d3, we would have 3d3 as the electron configuration for vanadium.
Yeah, so we always take away one level of whatever period we're on. So if we were at zirconium, because that's in period 5, that would be 4d and then 2, because it's the second one over.
So at this point, it really becomes just a matter of practicing them. Do them yourself, struggle with them, and then look at the answer, and go back.
Yep, that's basically it when it comes to that. Let me know if you have questions as you're going through those, and we'll kind of continue on where we're at for looking at electron configuration a little bit more in depth. So what we have here is what's called orbital notation. What you saw with the 1s2, 2s2, 2p6, and so on is electron configuration. Orbital notation is kind of a visual for it. So you can see that we have 2 electrons in each of the what are called orbitals. 2p is a sub-level. The numbers in front represent energy levels. So in this right here, we have 6 electrons in the 2p sub-level, which is the second energy level. So in the second energy level, you have a total of 8 electrons. We see them as arrows going up and down from each other, kind of in opposite directions, because electrons want to repel, so they'd be spinning in opposite directions. Now you can see how this one up here is by itself, and I can't remember the person's name for the rule, but one of the rules states that the electrons need to be individual in each orbital before they're paired up. We see this a little easier in phosphorus. 1s2, 2s2, 2p6, 3s2, 3p3, and each of these will be individual before they're paired up. This is because electrons want to repel against each other, so therefore they're going to be in their own space before they have to be pushed or attracted to the nucleus and forced into an energy level, I should say an orbital, with another electron. Well, let's take a look at where this becomes important. So there are some exceptions to this guidelines, and they are in the D block. So when we have the idea that 4s2 is all filled up, you see 3d, this would be 3d4, but no, it's not. There actually seems to be an electron that has left the s and moved to the d. This is repeated in a couple different spots, and the reason for this is the fact that they will have lower energy, and the fact that they're at lower energy is the reason of why this holds true in that we see in nature. We'll talk a little bit more in depth about what's called penetration and shielding of why this occurs based upon the different electrons that can kind of jump from this outer s electron into the d, because you see that's what occurs for all of these, is these s electrons falling down to a more lower energy level, being able to penetrate to a lower energy level. There are some other areas that we can look at in determining and talking about electron configuration, and this deals with the noble gases. Group 18, all the way at the end, all these would have a P6 filled up. This makes them very stable. They don't react with other things. We call them inert, because 8 is great. Well, the idea is that you can see the S is electron, S2 is filled up for helium. There is no P for the helium. We get S2, P6, S2, P6, S2, P6. Note that D electrons are found at a lower energy level and therefore not included. When we talk about valence electrons, we'll talk about these as being the highest energy level. The highest energy level is energy level 4. So D electrons will never be what are called valence electrons. Now there's a shortcut method of writing configurations called noble gas notation. You need a element, let's say, I don't know, selenium, number 34 on your periodic table. The previous noble gas is argon. So going back, argon is going to represent 18 electrons, those core inner electrons, and you're going to replace that 18 electrons with just the argon AR in brackets. Then you have the leftover configuration. Think of it almost as a starting shortcut instead of always starting with hydrogen. So for example, lithium, which is your 1s2, 2s1. Helium is 1s2, so it gets replaced. You get helium 2s1. 1s2 for helium gets replaced. Helium 2s2, 2p3, the other outer electrons. And you can see the same is done for sodium using neon. They can get even bigger when you have some d electrons involved. But again, those d electrons are going to be all part of that. Barium's really big. Xenon goes up to 5p6. That's going to be replaced, giving your 6s2. Krypton also gets replaced, and you have the remainder. So it's pretty useful in looking at the outer electrons and what's going to be more reactive. But keep in mind the d electrons are never going to be part of the valence electrons. This is where we get into the ideas of shielding and penetration, the idea that makes those exceptions what they are. Chemistry is all about attractions and repulsions. In the form of an atom, you have the positively charged nucleus being attracted by the negatively charged electrons. However, the electrons are being repulsed by each other. So this kind of gives these different areas of where you're going to find electrons, often called orbitals. Now, shielding. Some electrons on the outside are shielded by what are called core electrons. Outer electrons are often called valence electrons. Core electrons are inner electrons. So the inner electrons create a shielding effect. They prevent the outer electrons from being attracted so much. Outer electrons really don't screen for each other because they're on the outer edge of the atom. So they can't really get in each other's way if they're just next to each other. Because remember, what they're attracted to is the center nucleus. Now, shielding causes the outer electrons to experience not the full strength of nuclear charge, which makes them less attracted, which makes them more likely to react. This is called effective nuclear charge. So you have the actual nuclear charge, meaning like how many protons are in the center, and then the number of electrons in lower energy levels, kind of the ones that will contribute to shielding. This is going to help us explain why we have the exceptions we see and later on periodic trends. So this effective charge is going to be part of your explanations you'll talk about. And there's a trend in the shielding strength. The ones closer to S, then P, then D, then F. So S is going to shield the most because they're often the core electrons, then P, D, and F. So let's just take a little example. You've got lithium with its 3 protons in the center. It's got 2 core electrons and 1 valence electron, so the effective nuclear charge on this electron is going to be 1+. So that's what we would think to experience it to be. However, that's not always the case. Of course not. That's you'll find as a running theme out in chemistry. Penetration is when it actually gets closer than it normally would at its outer boundary distance. There are different orbital shapes. We don't go into them because they're not relevant for AP as far as knowing the shapes and what they look like. But if you go Google what S, P, and D orbitals look like, you see they have varied shapes. But you also see they also spend some area very near the nucleus. This is their penetration areas. So some electrons will have a higher density closer to the nucleus, and when it penetrates, it's going to experience a higher than the, the effective charge that it did when it was shielding. So an orbital is the region in which the atom can be. Again, it's just a probability of finding an electron. They're not 100%. Orbital shapes are defined by 90% of that electron ability. You're looking at an S shape, you can see that there's kind of some fuzziness, darker in the center, a little bit lighter, much lighter further out. And it makes sense that you have a higher probability of an electron being present the closer it is to the nucleus rather than further. However, these orbitals are not just solid spheres. There's what are called nodes, areas where you're going to find nothing present. So 1s, 2s is larger, but there's an area where you're not going to experience electron density. 3s is even larger. Again, these are the nodes where they're not going to be found as far as the electrons go. So when we look at this idea of penetration using a little graphic representation here, this is the most probable distance. So this is like the normal regular orbital distance for most of the electrons, or most of them at the time. And then we can look at there's some areas of penetration, 2 areas in fact, in which the nodes are going to be where there's no penetration. There's no radial probability of electrons. So we can tell this is the 3s because there's 2 areas of penetration of where those would be, hence the 2 nodes as well. As they get larger, there's more areas of penetration. So 3s is going to have 2 areas of penetration, while 2s will just have 1. This idea is that these provide the areas of which these electrons can be jumping from one area to another. So the closer to the nucleus, the more attraction it experiences. That makes sense. That's Coulomb's law of attraction. The better an outer electron is penetrating, the more attraction it will have for the nucleus. That makes sense too as well, because it's closer, therefore it's going to be experiencing more attraction. Now the degree of penetration is to this radial distribution function. Don't look too far into that. The idea is that this tells us that they're closer distances, they're going to have a higher probability of it being there. So the differences between penetration and shielding. You got the 2s orbital penetrates more deeply into the 1s orbital than the 2p does. When you look at the 2p, there is no penetration. You see that there's penetration of the 2s, though, but there's nothing for the 2p. So the idea is that the 2p experiences less attractive force, therefore they're shielded, which makes sense because the p orbital is outside of the s orbital in the second energy level, so it's going to be shielded by those 2s electrons. The penetration of the 2s means that it's going to experience more attractive force, therefore less shielded from the nucleus. This also deals because it's closer, it's going to have less electrons kind of in front of it as it goes towards the nucleus. So what this all summarizes as is the same pattern for each of these. Penetration towards the nucleus, S is the best, F is the worst. And they go across the periodic table, S, P, D, and then F is in the center. We rarely even talk about that at all. Attraction for the nucleus, the S electrons most attracted, P less, D even lower, F the least. Shielding they contribute, S is going to get in the way the most, then P, then D, then F. So they're really in the same pattern, and this is going to help us explain and talk about these as they come up in different questions. So this is one of the AP areas where I want to hit you up with some good techniques so you can be successful there. The first off, don't use generic terms, specific terms. When you say it's shielded more, that's vague. What is shielded more? Calcium's valence electrons, shielded more. Okay? So the idea is you also must reference both atoms. If they're talking about, these two things like calcium and what's the other one, sodium, you need to show which one is which, not just be vague. It's just like listing off anybody or anything around. Don't use the generic pronouns. Use the actual elements or molecules that are talked about. Those are the things you want to be clear about so it's clear to your reader, because they're using a rubric, and if they're missing some key parts because you were vague, therefore there's some points that you're going to be missing. You must give reasons. Don't just say what is occurring. They always want an explanation of why. Okay? But it doesn't have to be super challenging, right? Because calcium's valence electrons are in the 4th energy level. There's 3 other layers beneath it. Therefore, calcium, with its shielded from 3 levels of core electrons, sodium's only shielded from 2. But you can see I named all of the elements. I gave numbers. Don't just say one more. Tell me how many more. It's not much difference, but it gives that to where you might get a point where you wouldn't have if you were vague. Last little bit, be succinct. That means to the point, together. If you look at a lot of rubrics, as I've recommended to do, you'll see that they're not like 40 different paragraphs of explanation. They're actually very short. Don't ramble. I do, but you don't try to do that. Bullet points are your friend because they can help be organized in your thoughts. Keep a grading rubric in mind, making sure that you have attraction to the nucleus, repulsion between the electrons, because those are the 2 avenues you're going to hit the most. Don't just drop in some terms. You have to use these terms to explain. So these are proper vocab, but don't just say, it's because of shielding. It's because of the lower effective nuclear charge. Describe in a sentence or 2 what that means, because that's what you want to hit when you get to these. All right, let me know what kind of questions you have. I think that's the end of this one here. No, a little bit more. Remember, this helps explain the effective charge that we see as we get into more of the exceptions to the rule, and we get into the idea of the periodic trends, the radius, ionization energy, all these exceptions that we kind of just glossed over. This is the reason why, and you'll need to be explaining those at some level on the AP test, most likely. Let me know what kind of questions you have, and I'm here to help. Take care. Talk to you later.